Hi guys, I'm Andy from Space for All Education. I'm doing this presentation on how to get satellites into orbit. Now we have a little bit discuss about what type of satellites and everything like that, and then we'll discuss on how to get there. So please enjoy, and I hope you like. And so this is where it all starts. And if you have any questions at the end or anything like that, please go to your teachers. You can message me at spaceforalleducation.com. Okay, so let's get straight into it. So the first thing we need to discuss is nice and simple. Let me get out of the way. Oh, we need to decide on what type of satellite we want and how high it's going to go. So this is really important, really crucial, because you don't put the wrong satellite in the wrong orbit. That'd be terrible. And we also need to decide on the type of rocket. Now for the ease of this presentation, we are going to decide on the rocket of the Falcon 9, the SpaceX rocket that's launching the Skylink satellites. Okay, so I will go through the different types of satellites and different types of orbits, but for this presentation I'm using the Skylink satellites for the SpaceX launch using the Falcon 9. Okay, so next is the assembly of the satellites and the rocket. Now this could take anything between 6 months and 3 years. Because Falcon 9 is now able to be reused, that process is speed up drastically and they can do regular launches very quickly. Then of course we have the launches. Now you can watch launches on YouTube, or you can log on to the SpaceX website. You can happily watch launches. There are regular launches live and you can see the whole process, including how they release your satellites. So again, the deployment, you get to see the satellites actually get deployed and how they drop out of the rocket and everything like that. You don't get to see this bit, but we do have to adjust for height, and then we test, and then the satellites are deployed and working, and then we have a brilliant Skylink network. Okay, but if we use a different satellite, that process is slightly different. So what type of different satellites are there besides the Skylink? Well, we have the communication satellites, which are the Skylink. We have remote sensing satellites. Now these remote sensing, you may think, oh, what are they? Well, they track ships, they track the sea level, they track the land migration, they track everything from animals to sea life to whatever. They can remotely sensor what's going on. Navigation satellites. Now that's not only aeroplanes and rockets and satellites and other satellites, that's also ships on the ground, sometimes your cars and everything like that. So navigation satellites are a different type of satellites. Global geocentric and geostationary satellites, I've linked them two together, I'm going to say them together, are very similar, but I'll go through them in a minute. Global positioning satellites, GPS, are similar to navigation. They're a little bit lower in orbit, but they're there for us. Drone satellites, well, you've all flown a drone, you know how they work, so it shouldn't be a problem at all. Ground satellites, how do we receive the signal? We're sending it up, we're sending the information up, we've got to be able to send it, we need to receive it back down. Polar satellites, now these are very different satellites because they've got to stay above the North or the South Pole, so they have a different orbit and require different power. Nanosats, CubeSats and small sats are very similar. They're not all the same, but they're very similar, and their lifespan is usually approximately 12 months. They are working on to increasing this to 3 years, but depending on their low orbit, they could burn up in the atmosphere very, very quickly. So we have to be aware of that. So you have to pick carefully what type of satellite we're going to use. So when I say what type of satellites, we're talking about what satellite goes in what orbit. So if we have a low Earth orbit, a geocentric orbit of altitude of 2,000 kilometers, 1,200 miles, these satellites are commonly used for communication, military reconnaissance and other imaging applications. Now when you say communications, we're talking very simple communications, your phone, your satellite phones and other things like that. But simple communications, nothing too difficult. Military reconnaissance, so they can communicate with troops around the world quickly, easily and efficiently. Other imaging, tracking military movements, making sure we're okay. You've got the Google Maps, so we can see what your house looks like from the sky. These are the types of satellites we use to do this, and they're in a low Earth orbit. Okay, the next one is the medium Earth orbits. Let me get out of the way. Geocentric orbits ranging from an altitude of above 2,000 kilometers, 1,200 miles, or just below the geosynchronous orbit of 35,786 kilometers, 22,000 miles, 263 miles above the ground. also known as an intermediate circular orbit. These are used for GPS, GPS, also other spacecrafts, Galileo, which is a telescope. GPS has altitude 20,200 kilometers, an orbit period for almost 12 hours. So they come around above us twice a day. So it's really important that we know what's in what area, and if something happens in that area, we need to know about it. So those are those satellites. Next is the high Earth orbits. These are ones going even higher up. These are geosynchronous orbits, above the 22,236 miles. Is a high Earth orbit that allows satellites to match the Earth's rotation. Okay, so they can stay at a fixed point above the equator, in a position to available monitoring weather conditions, communications, and surveillance. Now, this is where I went geosynchronous and geosynchronous and GPS. One will go round the Earth and constantly monitor it. The other will be a fixed point and it will stay there. So depending on the orbit you get, depends if it orbits or it stays there and follows the Earth around. So they are very important. So just to go in a little bit more detail about geosynchronous orbits and geostationary orbits, that's the one I was trying to say, are orbits around the Earth matching the sidereal rotational period. Although the term is often used interchangeably, technically geosynchronous orbits match the Earth's rotational period, but does not require a zero orbital incline to the equator, thus does not match a stationary above a given point to the equator. Thus, geostationary orbit is defined as geosynchronous orbit at zero incline. Geosynchronous orbits, or geostationary orbits, have a semi-major axis at 26,199 miles. Okay, so there's a big difference, but a little difference. Both complete one full orbit sidereal rotation relative to the star, not the sun. So what this means is, Earth is here. Let's get this in. Let me get in screen. We have the Earth here, and the satellite will be above us here. Where's my hand? There it is. It'll be here. So as the Earth rotates, it goes round. Now, if it is to the sun, remember the sun sets and the sun rises, so it wouldn't be in the same position. But if we do it to the stars are so far away, we can use that as a more fixed point, so we can orbit correctly, and the satellite will stay in the correct position. So we make sure it's right. So that's why we have to use stars further away to do better here. Okay. Let me get out of the way again. We're now going on to the more important bits. How do we launch it? So we pick the satellites, we go for launch, and remember we're looking at the SpaceX ones. I will be attaching the slides on for people to download, and you'll see a short video. The amount of energy required to launch a satellite depends on the orbital location we're going to. So the higher we go, the more power we need. Satellites of high inclined orbits, such as polar orbits, take more energy than satellites that are in circular orbits around the Earth. Satellites in a low incline need help to boost into the orbit. The ISS, the International Space Station, has an incline of 51.6397 degrees to make it easier for space shuttles and rockets to reach it. Polar orbiting, on the other hand, gets no help from the Earth momentum, so requires more energy. So when we put a satellite, the ISS is absolutely huge. If we didn't keep it at a certain degree angle, it would drift off in space, but it would be very difficult to dock with it. And we need limited power, so we don't need to use lots of power to keep it up there. Yet, if we're going above the North and South Pole, because we're not using the gravity of the Earth's equator, not so up there. It's limited because it all comes from the middle. It needs more power to hold that orbit, so the satellites up the North and South Pole tend to be larger, so they can hold more fuel to keep those orbits. That's what that's saying. Okay, going on, we have the deployment. Hang on, sorry, 1 second. Deployment speed. Now, as I said, we're looking at low Earth orbit, so we're looking at 200 kilometers. Require an altitude of 200 kilometers. Now we said below 1,200 kilometers, so they need to need to get to a velocity of more than 17,000 miles per hour or 27,400 kilometers per hour to maintain an orbit of 22,223 miles above the Earth. Satellites orbit at a speed of about 7,000 miles per hour at a distance that makes the rotation in 24 hours, since the Earth's rotation is once 24 hours. Satellites at 22,000 miles altitude stay in a fixed position relative to the Earth's surface because the satellite stays in geostationary orbits. Okay, so you're a little bit confused by that, I know you are. Okay, so we first of all need to get satellites at an altitude of a minimum of 200 kilometers above the Earth. However, they will go round the Earth because they'll be traveling so fast, and they won't stay in a fixed position. We need to go much higher if we want them in a fixed position. So you've got to work out, do you want them low to Earth and they will rotate around the Earth, or do you want them really high up so they're not at a fixed point, so they stay at a fixed point, and they stay directly above your house and they never move. So we've got to be really careful where we put them and everything like that. And the little link there, again, your teachers will have that, will show you how the Starlinks are deployed after they are launched, and I'll go more into that in a minute. So how do we maintain the orbits? Once they're up there, how do we do it? Well, once the satellites are, it usually takes a little bit of work, but not much, because gravity is strong, and it will be pulled out of position by the Sun, the Moon, Jupiter, and other satellites orbiting throughout their lifetime. Those satellites have to move 3 or 4 times a year to keep their place. NASA monitors this and adjusts them accordingly. This is other people's satellites as well, so NASA has a lot of control over where the satellites are and how to do them. Other countries have their own countries that monitor satellites, but when they pass over their space area, they have to take control of them and move them, or they have to radio through and tell them to change accordingly. Because if a satellite goes too low or hits something else, it's going to eventually crash, and then it will go down to Earth, burn up in the atmosphere, and then we can't use it. So we've got to monitor and make sure they don't collide. Okay, maintain orbit. We'll do another bit on this, because this is important. Atmospheric drag is strong when the Sun is active. So when it's really, really hot, you think of, I'm basing this in the UK, I apologise if you're in other countries. When we're in the UK, when it gets really hot here, the atmosphere actually rises. Just like when as water boils, it rises up. So as the Earth heats up, as the UK heats up and it gets hotter, the atmosphere rises into the low Earth orbits, and that causes a drag force on the satellites in low Earth orbit. So we have a choice. We either move them or we leave them and we put a little bit more power into them so they can do that. Now, on February 11th, community satellites, both owned by uranium and a US company, collided with a non-functioning Russian satellite. Both satellites broke apart and into debris field, causing at least 2,500 pieces of debris. Now that has to be maintained because these can cause damage to other satellites, so we need to know where that field is and where it's all going and everything like that, so we can monitor it. A lot of it will be dragged eventually back down to Earth and burn up in our atmosphere, so we need to maintain to make sure accidents like that don't happen again. Okay, so how much space stuff is there to make sure we don't collide into stuff? Well, actually, there's a lot. Look at that. You can see that black dot in the middle. That's Earth surrounded by satellites. That's surrounded by satellites. That's not Earth without satellites. That's surrounded by satellites. And all those other little dots are more satellites. And believe it or not, 90% of these do not work. They're no longer operational. We don't use them. They can be reactivated when they recharge their batteries and everything like that. We may be able to save them, but a lot of them are dead. Only 10% of satellites are still in orbit today. So that's a lot of satellites that they need to be monitored, controlled, and adjusted for so we don't crash into them. So space, satellites, is very, very messy at the minute, and we need to tidy it up. So we're looking at ways to do that. Maybe you can think of a way to do that. So we've gone through the basics. I've crossed over things very quickly. So now we're going to go back and we're going to look at how to get a satellite into orbit. So I'm going back to this slide here, the launch. So what we do, excuse me, sorry, come here, is we have our big rocket. Let's hold this away so you can see it. We have an absolutely huge rocket, so I'm going to sit in front of the camera so you can see this. And that's got to get 22,000 miles per hour or higher to get off the Earth. So we've got to get quite a bit of speed off that. So we need a lot of power at the bottom to push it up. Now, remember, this is the Falcon 9. So when it reaches the right orbit, so we're going low Earth orbit, it comes apart. It doesn't twist. It comes apart. We have the big bit that you see on SpaceX. Where's the bloody camera? Sorry, it's white, so it's not showing. That goes back down to Earth. And then our small bit. Come on, show me the small bit. There we go. Put it in front of me. There we go. This small bit will hold your satellites, and it will go up. The top will come off. Now, for the sake of this, come on down. Come on, give me. No, we go this way. This is a manned section, but that just drops off. We don't need that. It's got, so that will be a lot smaller on the real one. This bit here will hold 60 satellites. 60. Now, when it's in orbit, it's also going away from the Earth. Now, the problem is, when you're up there, it's very different to when it's down here. So Earth is still pulling it down. So when it gets to approximately the right height we want, which is below 1,200 kilometers to miles, sorry, we rotate it ever so slightly, so that way we allow the Earth's gravity to pull us into orbit. So we're still moving at the same speed, but the Earth is pulling us into orbit. So we circle round and we stay there. And because there's no drag, or there's limited drag, we never slow down. That's how satellites stay out there, is because they never slow down, because there's no drag to stop them and force them down. On Earth, if you're spinning a bucket, if you spin a cup, a bit of sand in really fast, it keeps going. But when you stop, the gravity pulls it down very quickly and it stops. Up in space, the gravity is strong enough to pull it down, but not strong enough to pull it into crash. But because the speed is moving so fast, it will keep spinning and spinning and spinning. And the satellites stay up there for a very long time. Hence why we have so much up there at the minute. So that's how satellites go up. They go up, and then they have to incline to keep the orbit, but they keep their speed. And then they keep rotating round and round and round. And they can be up there for many years. We have lots up there. Okay, so I think that covers how to launch a satellite. If you have any questions, please ask your teachers to get in touch with me. I'm happy to answer any more questions. You can comment below on the video if you want. It's completely your choice. It's a YouTube link for the teachers who have used it. If you are in the Milton Keynes area and you feel like you need more answers, come to my Water Rocket Family Fun Day. Bring your own water rocket down. We'll launch it for you, and you can have a lot of fun launching water rockets. But I will be there to answer any of your space questions and help inspire you. There'll be other space companies there as well to encourage you about the space industry and your futures in it and what you need to study. So please, if you're in the Milton Keynes area, come on down. I'd love to see what water rockets you come up with and everything like that. Thank you so much for your time. Thank you so much for your patience. I hope you've enjoyed this presentation. And remember, if you have any questions, please get in touch. Andy at Space for All Education. Check out my website and have a great, fantastic day. Thank you.